Hello, hello, hello. Okay, just a minute. Okay. Okay. Hello, hello. Yeah, so I am audible at least. Okay. Let me put up the context. Okay, what we are going to do and what is this stream about. Okay, firstly, and I will directly jump to the topic that we are going to study today because I don't want to waste any more time. Okay, I know I'm a little inconsistent in this YouTube. Okay, and doing streams. There are some personal reasons I was not able to concentrate on the YouTube because I was doing something which I can't do on the YouTube. I was also learning from the YouTube, so my learning learning from the YouTube myself, and I'm doing some other tasks which is important. Okay, so I was not able to be consistent, or there are some procrastinates and habits that I does do, but let's just not go into it. Okay? Let me show it to you what we are going to do today. So yeah, this is what we are going to do today. We will be learning some of the topics regarding the recommender system. I have something. I have a test or a you could say a exam tomorrow, which for which I have to prepare. So I don't want to break my consistency because of these things. That is why I thought of why not do this stream regarding these also. Okay? So yeah, I hope this will help you also. Okay? So yeah, let's just start. Okay. So we laws of text. Okay? So these are the PPT that have been saved in our college. Okay? So it is from the University of Edinburgh. The lecture's objective: learning about some. Okay, we can do one thing. Okay. Hmm. Let me set something up here because I have an idea and okay, though this is not possible. Okay. Okay. So yeah, I think it is not possible in this. So we have to do it this way. I thought of why not making notes regarding these also, so that after I read everything, I will be able to revise them also. But the thing is, if I don't want to log in eraser.io from this Gmail, okay? And in another Gmail, the PPT will not open. So yeah, let's not waste the time and learning about some tax law. So these are the tax law. One of them was Zipf's law, and another was Benford law, and another was Heap's law and clumping context. So we will be going through what are these terms and what are these laws. Okay? What the what the what? So we will be going through with these. Okay? Cell command is cat. Why is this keep happening? Okay. Cell command is cat sort unique I don't know about gree. Let's just search for this gree command in Linux. Alright. What does it does? We can do this unique. So we can do what? What are these? To remove the duplicate line from k dot this we can use this. Okay, so this will only print the okay, so single line. Let's suppose uh, if we have this as a context. Okay, let's suppose Okay, why is this keep happening? Okay. So let's say we have kt.text and inside which we have this is what written inside it. ठीक है, तो if you wanted to print the unique lines, ठीक है, if the line does repeat in this txt, ठीक है, तो it will not get printed, ठीक है, it will just print the unique line. Let's suppose if this line I love music is three time in this kt.txt, it will be printing in a only one time, and another time it will just ignore it this. And yeah, it I think it apply for only the lines. Let's suppose if we having I love music, and then again in the same line if it is I love music, it will get printed a whole line. Okay, so yeah, that is what I can understand from this. Okay. Hmm. So we can do one thing. I have another ID in this which I can able to log in also. Okay, so I think maybe we can do this. Yeah. Hmm. Okay, it is taking some time to load. Okay. Uh, what is happening? I don't know why. Uh, Never mind. Okay. So we will be making notes in here. I'll try making notes. Okay. I think. Is my net is not working, or what is the what is the case? I don't know. Why is it so laggy? I think it is working now. Okay, it is working. Can I zoom? Okay, I can't zoom anymore. I think this is the yeah. Okay. So we will be making notes also over here. Let's let us like this laws of these are all the laws. We will be seeing them one by one. What are words? Words are nothing. Words are basic unit to represent the text. So that is a simple statement. Certain characteristics are observed for the word we use. Okay, so we can observe certain characteristics with our word. Let's suppose if we are saying a particular thing, and we are angry, so we will be saying something rude maybe. Most of the people does that. Okay, so yeah, these are some characteristics that we can find out from our words. So words are great. Words are great when we wanted to characterize something. Okay, so these characteristics are very consistent that we can apply law. Yeah, this is a very small example that I have given to you. Okay, there are much more things that we can characterize with the help of words, because human does a certain thing in a certain way. So yeah, these law apply for different languages, different domain of text. Okay, that is okay. Frequency of words. Some words are very frequent. Okay, so yeah, that is true, because these stop words we uses much more time than the words, because it does appear in a, let's suppose if we are writing a paragraph or maybe writing a book or anything, any article, ठीक है, तो we will be using these stop words much more time than the a particular word, ठीक है. Many words are less frequent. Let's suppose this word could be a less frequent. Yeah, so that is true. Let's suppose if you are referring to something, you are referring to a place that you have visited and you are writing a blog, it might be come once or twice in your article, okay. 50% terms appear once, okay, so 50% terms then appears in word. So this is a reference of I think this thing, okay? So this is a reference of this in this in yeah, this is the thing it is referring to. All the conclusions, all the statements that has been written over there, it is from here, the Bible, okay. Okay. 50% of term appear once, ठीक है, तो the 50% of the terms are appearing in once only, and frequency of word has hard exponential decay, okay. So this is Zipf's law, okay. So these are all the laws. I will be writing it down over here. Why is this? Okay, I need to convert it into a text. I think I can do one thing. Okay. It looks good. For a given collection of text and ranking unique term according to their frequency, then okay. So let's suppose if we have a collection of text and we are ranking the unique term according to their frequency, like how many time it does appear a unique term, ठीक है. Let's suppose of we are ranking it how much time it does appear. So rank is directly inversely proportional to probability of that word. Is that what they mean? Rank of the term according to frequency is inversely proportional to probability of appearance or probability of appearance of that word. That is true. We can copy this thing. We can write it over here. Okay. This is the formula. I could do it like this. We can. Okay. This is the formula, which does mean that it is inversely proportional to the probability or the frequency. So rank does. So the higher the rank, let's suppose if a certain word, okay, so we are counting it like this, right? Let's suppose in this diagram. Just keep happening to me. I don't know. We can do one thing more. We can just increase the size of this thing. This looks good to me. So what is happening over here? Okay. Let me go little down. Let's suppose the rank of the, okay, so yeah, so the rank, let's suppose if a rank is 1, which is a less number comparatively to, let's suppose if we have a unique word which is coming only once, whose ranks must be a very at the very last, okay. So comparatively to that word, this is less, ठीक है. तो which is coming much quite much time, ठीक है, or quite frequently, ठीक है, तो its probability will be higher. As you can see here, let's suppose D is coming इतना time in a given corpus, in a given any text, ठीक है, तो its rank is 1, which is a less rank, ठीक है, और less number wise a rank is higher obviously because it is 1, but number wise it is less, ठीक है. And let's suppose we are comparing a number which is having 16 and its rank is lesser, so yeah, that is why it is inversely proportional to this. So yeah, that is all I think practical. Okay, we have this Bible, so in which there are 8 lakh 24,054 words, and okay, so we do not need to be aware of this concept. Distribution of first digit in a frequency. So this is okay. Are they asking us whether this is a uniformly distributed, normally distributed, or a skew? One, let's suppose the one is having a high probability, then the probabilities keep decreasing. I think it is exponentially decay. This is the right one, I think. At least that is what I thought too. So because the probability for the rank 1 is higher comparatively to other, and after that it is keep decreasing. I think it is a question. So let's just, we have answered it here. Let's go to the other one. First digit of the number zips like law. Okay, first digit of number follows a zips like law. Term frequency, physical constraint, energy bills, population number. This is obviously Benford law. Okay, so it has not explained itself, so we will be going to check gpt.com. Okay, we will be explain this in okay. Benford's law says in many real life data set, number does not in real life data set, number does not start evenly with digit 1 to 9. Okay. Instead, small digit like 1 appear as the first digit, much more like the bigger one like 9. Okay, so it is saying, okay, so in a real data set, let's suppose if we are taking a data set which is related to a number, let's suppose uh, we have a data of something which is giving a priority which is having a number. Okay, so what happens in that particular thing? Smaller number, let's suppose 1 to 5, which could be considered a smaller number comparatively in 1 to 9. Okay, so smaller number like 1 appear as the first digit much more. Okay, so first digit could be 1. Okay, but first digit can be 1 most of the time. It does not mean that 9 does not come so often. Okay, so but there was because this is somewhat related to that thing that I have shown to you. I think this is the one. So whenever a number is starting, let's suppose it is starting with 1, right? So that is why these all statements are somewhat related to this thing. Okay, so you can refer it. You could just have to go through this URL here if you wanted to watch what is this content about. But yeah, this is something that is appearing much more time than comparatively to the other as a first character. Okay, so if numbers were random, then you might expect one appear 11%. Okay, so if number is random, let's suppose if you have no idea about whether a particular number is coming how much time, how many time. Okay, so you just consider it that it is coming to 11% time, because yeah, that is what happens. Let's suppose you have a 100% probability, even though let's suppose you are saying 99% probability. Okay, so for let's suppose 1 to 9, what do you think is probability of each character? Each number have probability of what? 99 by 11, right? Sorry, 99 by 9. So which is 11%, right? This is how it is calculating it here. And but in reality it appeared 30%. So yeah, but in reality in this particular document what is happening, it is not following this thing, and it is appearing 30% of the time. Okay, in this document which is a Bible document. Okay? So number prefer starting with 1. Okay, easy example, population number. These are the easy examples. I just wanted to rate the formula. Why does this happen? Because many real world number grow multiplexly, not linearly. Okay, that is true. Span many scales. 1, 2, now. The natural creates more number starting with 1. This is the formula for calculating these things. So where D is what? D is the first digit. Okay. Okay, they have come up with this formula to calculate probability of each digit. So let's suppose if we are talking about the digit 1, and for just for the context I just wanted to clarify, they are talking about the first number in a digit. It is not about appearance of the particular number 1 to 9, how much time it is coming in all the corpus. Okay? They are not talking about it in a particular words. What are the first digit? That is what they are talking about, and that is 38% according to this formula that they have created. Okay? Let me do one thing, and let me do we have okay, we do not give me Okay. Somebody have texted me. Pangu Changi Sun. What? I'm just studying about recommender system. If you are aware about it, okay. Uh, you can check out my different stream if you don't want to study this, because I also don't think because this is somewhat useful. I'm just doing it because I just wanted to consistent. I don't wanted to break the consistency that I'm doing consistently. Okay. At least that is what I'm consistent, being consistent of, breaking the consistency. So I just wanted to break being consistent on this YouTube. So that is why I'm just doing this stream. Uh, and it does help, okay? Because let's suppose if I am reading a particular book or particular article, okay, it uh, it does clear a bit in my mind, but if I explain it to someone, it get much clear and I can remember it much longer, okay? And I'm also making notes regarding this, so that is what a good thing to have, okay? Let me do one thing. We were okay, yeah. So we were okay. Just give me notes. Okay. Okay, so we have studied about these laws. Okay, the first one was to the probability will universally proportional. Okay, so I don't think so. We have this escalation mark. We do not. It is R, probability of R. Okay, so we'll just edit this thing. Okay, it does look good. Okay. So it is inversely proportional to the rank will be inversely proportional to the probability of that word. Okay. Then we have a study about the Benford law in real life or in real world data set. The first digit follows a logarithmic distribution where the smaller digit of a pair of n. Okay. So this is the formula. If you wanted to calculate, you can calculate. We have studied about these. Then we were yeah, so now we have heaps law. Okay, so what it is, let's just read this. While going through the document, the number of new terms noticed will reduce over time. While going through the document, the number of okay. So as we go forward, let's suppose we have crossed the halfway or the 75% of the document, we have covered that much. After them the probability or the occurrence of new word will be lesser and lesser, ठीक है, because we must have like covered most of the words that has going to appear. Yeah. For a book or correction while reading through records, n is the number of word read, ठीक है, तो let's suppose n is the number of word read and b is a new word or a unique new word, ठीक है, a unique new word. Vocabulary growth, ठीक है, तो what this is the formula to calculate the vocabulary growth, ठीक है, तो how it grow exponentially kind of. This is the exponential graph, okay, exponential okay, no, it is not an exponential very yeah, it is a logarithmic graph, ठीक है. Let's start from this. So yeah, we get a logarithmic graph, ठीक है. So this is v of n, kb is this here, where b is less than 1 and typically b is 0.4 to 0.7, okay. But what is b? They do not have explained about what is b, right? Or do they? I don't think so. They have explained us what b is. Okay, it is given. Is that the case? Because I think it is given over here. I don't know where did this b come from. But they have given us b. I don't know. Let's do one thing. Okay. Let's copy the what is the answer is. Okay. B in Gibbs law is a constant. So it is a constant that control how fast the vocabulary grows. So I think it is kind of a learning constant or a part. I can if I wanted to relate it with something, it is a constant number, ठीक है, तो this number will tell how much the vocabulary grow over time, because yeah, this is a major factor I think. B shows that the new unique word growth slowly than the total word, typically 0.4 to 0.7, or this is the and this is how you find why did I okay, we can do one thing. Okay, let me okay. We do not require the formula because we can put it directly over there. Okay, so we get this. So we understand about these things. We learn about what is this law, Zipf's law, what is Beaufort law, what is Heaps law. The Heaps law is telling us that over some time, that suppose after some time, the growth of introduction the new word will be decreased here. So it is kind of a logarithmic graph here. So we get this thing. Okay, we can just copy this thing. Let's see if it works. Okay, it works in some way, but not the way I want it. I have to fix it. Okay, we need to put this over here, and we have what? It is not okay. So it is power B. Okay, we can define power like this, or we can define the power like this also. This looks good to me. Okay. B is okay, we got this. Okay. So this is the formula. Okay. Or we can do one thing. We can just write it this way. Just not write. Okay. Okay. We get this. Okay. So these are all the laws that we needed to be aware of. Okay. So this is the diagram for it. Okay. We study about these heaps laws. So shouldn't it saturated? Okay. This. Cause 2 became through, so shouldn't it be saturated? Already sobered to the extent that nothing could be filled up. Okay, so 80 plus million, but still growing. Okay, accurate for most collection, but different key be not very accurate when n is smaller. Okay, so this is coming because we have a large corpus of words with us, because we have, I think they have tell us that we have 80,000 or what, we have 8 lakh, sorry, my bad. We have 8 lakh words in this corpus, so we were able to really come up with these insights. But if we have less number of words together, we might not be able to see all these things into this, because we require data to analyze, we require data to come up with analysis, or come up with a solution, come up with a formula. So that is true. Clumping and catecon in the text. For Zipf law, we notice most words do not appear that much. Okay. Yeah, so we have studied in the Zipf law. Zipf law is what? Zipf law is about ranking, though ranking is inversely proportional to the probability. Some we have seen in that particular part that most word does not appear that much. Once you see a word once, expect to see again. Word are like rare Coggis disease, not really independently lightning. Words are rare event, but they are contagious. Contagious. Spread from one person organism to another, typically by direct contact. Likely to spread. Likely to spread. I think this is the meaning in our case. Word are rare even, but they are contagious. They does spread. ठीक है. A rare contiguous disease, not really independent lightning. ठीक है. Clumping and contagion in text, wiki, abstract collection, identifying term appearance only twice. Identify terms appear only twice, measuring the distance between two occurrence of terms. Let's suppose this. Okay. I think, okay, though I got this thing. Okay, so we in this what we were doing is let's suppose if a word comes over here, okay, so there is a high probability it does come after some time. Okay, that is what they are stating at the very least. That is what I was able to draw the conclusion out of this thing. So identifying the term only twice. Okay, identify terms appearing only twice, measuring the distance between two occurrence of the word. Let's suppose if it is coming over here and this is the second word. Plotting the diagram. If you plot the diagram, this is how it should be looks like. Okay? So majority of the term appear only twice. Twice appear close to each other. So majority of the term that does appear, okay, so they appear twice. Okay, so there is a high possibility over here that the term will appear again. Okay, I think that is what this means. Okay, just give it to this also. Let's make note. We were able to finish this thing. I think they have given us some resources, but we do not require it. These are the summary application of the law. So let's just, do we have anything else? No, right? We have covered this thing. And given a word of 20 billion terms, what is the number of unique terms? So this is how we calculate. Apply the law. Given a number of 20 billion terms, what is the number of unique terms? Do we have to apply this in this? I don't know what they expect from us. Heaps law, VNEQ, assume k equals to 0.25, b equals to this. So if we calculate it like this, we have a number of what is to 20 billion. So 20 billion is, I think, 1 billion is, I think, 1 crore. Is it 1 crore or what? 1 billion is almost equals to crore. 100 crore. 1 billion is 100 crore. That is so much fucking money. But yeah, 20 what? What am I have? 2000 crore. 2000 crore. We have 2000 crore, and if we have get the exponential of that thing, let's just uh, I don't even know how much. 2000 crore. Okay, this is 2 lakh. We add two more zero, then this will become 2 crore. Then we add 2000, right? Yeah. So we add 30 more. 1, 2, 3. Okay, this is how it should be. So we have power. Okay, we have power, and this 0.7. Okay, this is what comes up. Okay. Then we multiply it with 0.25. Multiply with it 0.25. So we get what? Okay. Is this how it should be? 40 lakh 61,261. What is the number of term? One number of term appear once. Okay. Okay. So we are able to get this with the help of Heap's law. And what Heap's law was? It is okay. Okay, it is the occurrence of words. So what is the number of term a pair of words? So how many terms does a pair of words? So for ones, do we have a formula? I don't think so. We have a formula to calculate what is the number of terms a pair of words. Let me search it over here. What are they expecting from us? Okay, so it is a conclusion from, I think over here. Where was it? Okay, where was that? I think it should be somewhere here. I don't know. It should be there, but never mind. We using this and try another language. Okay, text following this. Okay. We were able to understand these things. Okay, we got it. Okay, we have covered one PPT. Let me start from this. We will be taking a small break. Okay, I will be back. I am audible on the stream, right? I will be checking it for 1 minute. Why can't I unmute myself? What? Why is this thing lagging? myself. I can't select anything on this OBS. I think something goes wrong with the OBS. What the heck? I'm audible on the stream. Hello. Hello. This is the second time. That is why I don't wanted to do these streams, because I think I will be ending the stream with what can I do, yeah? It is not running. Bye bye. Good night. Okay, it is not even responding now. What?